Hi, everyone. Welcome to this week's stream for the Golden Path to Spring One. We're already up to number 5 now, so I'll post that in all of the chat things so you can see. If you want to see more about this episode, I guess it's down here. Just tanzu.tv/golden-path/5, and you can also see all of the other ones that we have upcoming as well. So yeah, today we have Denis, Magda from Gigabyte, and want to tell us like a little bit about yourself? You're muted.
Sure. Why not to mute myself? All right. Yes. So, hello everyone. If to briefly introduce myself, let me actually use this slide because we are going to talk about geo-distributed application journey. And when it comes to me, I've been working with distributed databases and systems for the last 8 years, primarily in the database segment. Presently, I am with Gigabyte that develops GigabyteDB, a distributed SQL database. Prior to Gigabyte, I contributed daily to another distributed database named Apache Ignite. That is designed for high performance and memory computing. And before all of those distributed system and databases, I was on the Java development team at Oracle and at Sun. So combining this experience of distributed systems and building real applications on Java, I'm going to share with you an interesting story and practical patterns on how to build applications for the cloud that can withstand various cloud outages.
Yeah, so if you have any questions, yeah, sounds great. And if you have any questions, please ask in the chat and Dennis will be answering them as well. And yeah, so basically today's title is Weathering the Cloud Storm, Building Resilient Geo-Distributed Apps with Spring Cloud. And we'll be continuing these up until we have the conference for Spring One, which is in August. At the end of this, I'll show a little slide that'll tell you a little bit more about that. It'll be in Las Vegas, connected with VMware Explore. So yeah, I will let you take it away.
All right, let's go. We are skipping the first 2 slides. We have already, crossed them out. And to begin with, high availability and how to weather different types of the storms in the cloud, or under the storms, I assume outages. Let's define geo-distributed applications. If you open Google, or if I think you go and ask ChatGPT what a geo-distributed application is, it's highly likely that you will find this definition. A geo-distributed app is an application that spans across multiple geographic locations. For what reason? For high availability, performance, and compliance. And we are going to cover the high availability feature of those applications today. Also, with this slide, you might have a question like, it looks extreme to me. I'm not actually developing applications that have to function across all of the different continents. But anyway, this talk is still for you if you're creating applications that are deployed within a single cloud region, but across multiple availability zones, like on this slide, right? For instance, your application can be hosted in the US West region, and the instances of the application run across 3 availability zones. That's also a geo-distributed application, my friends. At the same time, your application might function across your country. For instance, if you deploy your application instances across United States West, Central, or East region, that's also going to be a multi-region geo-distributed application, right? So generally speaking, geo-distributed app is an application that spans across multiple geographies, and a geography is a subjective thing. For some of the applications that can run across continents, spanning across the United States, Europe, and Asia. For some of the applications, it can be, just multiple application instances deployed within a single cloud region. But in any case, those are geo-distributed applications. And the next question is, why would you bother building those types of applications? Remember the first slide? Those applications are designed for high availability, performance, and compliance. We today are going to discuss high availability. Let's imagine that you and I, we are founders. We founded another startup company, and we decided to build another messenger, like Slack-like messenger. It's highly likely that you either use Slack or Microsoft Teams at work daily. And suppose that we decided to probably reinvent the wheel, or we have some secret sauce in mind and we want to feature and release this application. So we coded this application for like half a year and we released the first version of our Slack-like messenger. So right now the messenger is deployed somewhere in the US Central or even South zone. We have a database node, we have an application instance. That application instance can be comprised of multiple microservices, and we've got several customers. On the first day of the application release, one of those customers is Mrs. Blue, a financial advisor from New York, and she enjoys our application. She finds it, like a breakthrough. So we are on the right track as founders. But then a couple of days later, what happens? A major storm in that region where our application is deployed takes down the power grid, and that power grid takes down all of the cloud regions in that location. And our application is down, everything is down. Mrs. Blue and other thousands of users who joined our Slack-like messenger are disappointed. But again, those are the early days of our startup company. It didn't even bring a big impact on our reputation, but at least we as founders, we learned this lesson. Now we know that if you want to build an application, and an application that has to function in a distributed cloud environment, we need to do this somehow differently. And this is going to be a talk about this session, and we are going, apart from the slides, I'm going to spend most of the time showing you how to deploy a geo-distributed application in the real cloud environment. And we are going to experiment with the fault tolerance characteristics as well. So now let me put this slide, because it's very important. When we usually talk about cloud is a wonderful environment because it comes with abundant resources. We can literally deploy virtual machines or run different cloud services in pretty much any location of this planet, or at least on any continent except for Antarctica, right? But also, even though that environment comes with abundant resources, it's still prone to errors. It's prone to failures. If to judge by statistics, a major cloud failure or outage happens at least every 50 days. If to take all of the cloud providers as an example. So for instance, one day a major outage can be experienced in the AWS. In the next 50 days, a major cloud outage can be detected in IBM Cloud. Who knows? But generally that happens. You just need to be aware of that. And when I'm talking about major cloud outages, this is something that can bring down a complete cloud region. Minor outages that usually happen within one cloud availability zone or another, they happen all the times. That's why like every cloud region comes with at least 3 availability zones. But major outages that can take down an entire region also are becoming a commonplace, and they can happen. So you need to be ready for that. And you can do this experiment. For instance, several months ago, when I was preparing the slides for this talk, I decided to Google cloud outages, and this is what I've seen. Try to run the same experiment and see what cloud outages took place in the last day or two. And probably you will be surprised. But anyway, what can we do about that? By taking this whole information that cloud is large, comes with abundant resources, but also it fails, and it fails rather frequently. What should we do? What's our action list? First, accept the fact that a cloud outage can impact your application sooner or later. It can happen, let's say, to us in a week. It can happen to us in several years, but no one is protected. Every service, every application can go down if you do not deploy in a geo-distributed fashion. And if you accept the fact, then deploy and design your applications with multi-AZ or multi-region deployments in mind. So when you create your application, at least make sure that it can function across multiple availability zones. With the multiple availability zones configuration, you will not be able to withstand region-level outages, but at least you will be able to tolerate zone-level outages, which is also a good thing to have in your architecture. Another frequent question that I'm being asked whenever we have this discussion about geo-distributed applications and high availability, how about hybrid cloud deployments? If, let's say, Denis, you're telling me that cloud regions fail and cloud availability zones go down, then should I deploy across multiple cloud providers? And I share the opinion of Lydia Leon. She's a wonderful analyst. She said that before you even fantasize about multi-cloud for high availability, you should be multi-AZ in multiple regions and have maximized your resilience through proper application design implementation. So the point is that for the high availability, in my opinion, it doesn't make sense, just to deploy across multiple cloud providers. There are different reasons when you would go multi-cloud, but probably high availability is not the right choice. Because take this example. If a snowstorm brings down the power grid in one of the states, then all of the regions of any cloud provider in that state will be down, right? Doesn't matter whether you run on AWS or Microsoft Azure or Google Compute Engine, everyone will be impacted, right? So now, we as startup founders who created that Slack-like messenger, we learned all this information. Now we know that yes, cloud is a wonderful environment to deploy and move really fast with our startup company. But also we have to care about the high availability. We want to make sure that our application is up and running even when an outage happens in the cloud. And in our new architecture, in our new configuration, we are focused on the United States market right now. That's enough for us. And we are deploying multiple application instances across the country. So Mrs. Blue, and also a benefit of this architecture, apart from the high availability, is that application instances can serve user traffic from the location that is closest to your user. For instance, Mrs. Blue, you remember she lives in New York, financial advisor, and we have an application instance that is deployed nearby, which means that your application requests will be handled by that application instance, which also opens a little bit different conversation of advantages of geo-distributed app related to performance. But again, that's a separate topic. And now what happens if that region where Mrs. Blue application was connected to goes down, then it's not a big trouble. It's no longer a big deal for our Slack-like messenger, because all of the requests of Mrs. Blue will be forwarded to another application instance that is deployed in a completely different cloud region. So we made it, right? But that's, let's say, from the storytelling perspective. Now let's get down to business. Let's see how do we build such applications that can function across multiple cloud regions, and what's the easiest way to do that, right? What's available to us? Generally speaking, building blocks or components of geo-distributed applications, they are the same as you would have for your standard applications. Under standard application, I assume an application that functions within a single availability zone of a single cloud region. But there is only one difference between geo-distributed apps and standard apps. Components of geo-distributed apps have to be distributed by nature. For instance, we are going to look at the global load balancer that can be deployed, whose IP address can be deployed and available across multiple cloud regions. Also, your application layer has to be distributed. As on the previous slide, if you want your application instances to run across multiple regions, you need to make sure that your application can function this way. Also, many applications use different API gateways and data streaming layers if you need any synchronous or asynchronous communication within your solution, or if you need to provide some API layer to your customers. And finally, your database also needs to be distributed, because if you, let's say, even deploy your application within a single region, but across several availability zones, your database also has to function across multiple availability zones, because if one availability zone goes down, it will bring down your database and it will bring down your application instance at that zone. But if your application and database runs across multiple availability zones, that you're in a much better position, because you lose one zone, but the rest of the zones continue serving your data and traffic. All right. Also, this is the golden path to Spring One. And we are going to talk about Java applications, Spring Boot applications that we learned to build like many, I think, a decade or more ago. But when you create geo-distributed applications, there is one essential component that you have to keep in mind, and it's called Spring Cloud. Spring Cloud is a framework for building distributed applications in the cloud. So it comes with several projects or components that would simplify your configuration, discovery, and other capabilities whenever you deploy your Spring Boot applications across multiple availability zones or regions. For instance, if to list a few of the components of Spring Cloud, you have distributed configuration that can serve configuration for a particular application instance depending on its origin. Also, if your application is split into multiple microservices, then you can use service discovery so that each service can talk to each other really easily. You have routing, you have built-in load balancing capabilities if necessary, and many other components that are available to you. So generally speaking, your path from standalone or standard application that functions within a single availability zone to a multi-region one will be much easier if you use Spring Cloud, and also additional services that are provided by cloud providers, right? So our demo setup for today, because we are almost done with the slides. Our demo setup for today looks as follows. I'm going to use Google Cloud as an example, but everything stands true for other cloud providers, up to you. Then we will be using 2 cloud regions. Our solution will be deployed in the US East and US Central zones. The application is, as you know, a Slack-like messenger. So we will have basic messaging capabilities. We will have 2 microservices. One of the microservices is called Messenger. It provides the key feature so that users can exchange messages. And the second microservice called Attachments. So if a user wants to share a picture, then it will be possible to do through that microservice. From the Spring Cloud ecosystem, just for the sake of example, I selected Spring Config Server microservice. So that microservice also will be started alongside your primary application microservices, and it will be serving application configuration for your backend logic. But again, also for this use case, it would be nice to use Spring Discovery Service if you want the Messenger and Attachments microservices to talk to each other. But as long as I'm running my application instances in Google Kubernetes Engine, then I decided to reuse the existing discovery infrastructure of Kubernetes. But nevertheless, if you want to have something generic, you can always use discovery service. If you want to use API or if you want to use messaging, you have the messaging component in Spring Cloud. A lot of options. But Spring Config Server would be enough for us to show how Spring Cloud is used. And finally, the users. I'm going to be the only one user, but I will be happy to share with you an IP address of our multi-cluster ingress, which is the global load balancer that you can access from any point, and you will see where the traffic is routed. So the multi-cluster ingress, it will be routing our user requests to one of the Kubernetes clusters. And this is a big deal if you want to automate and simplify your manageability and deployment of these geo-distributed applications. So we are going to use 2 databases, 2 storages. Google Cloud Storage is going to be used for our attachments, for our pictures, and YugaByteDB, which is going to be used for our application data, such as users, messages, and blah, blah, blah. All right, so let's move on. Let's move on with the first step. And if you want to build a geo-distributed application, the first and the easiest step is to deploy multiple application instances, right? So before I do this, let me take the question from Alexei. I guess database replication also needed between zones. Yep, when you deploy your database across multiple zones or regions, you have to make sure that the data is available in those zones. And there are multiple, and Alexei, there are multiple, there is no any silver bullet solution for a multi-AZ database deployment. There are several of them, and we will review them in the end of this session. So stay tuned, because you can have synchronous replication, you asynchronous replication. It all depends on your requirements. You always will have some trade-offs with your database, multi-region or multi-zone database deployment. Okay, so let me switch to the console. Let's finally code. Not code, because the application is created. This application, if you are interested, I will give you the coordinates in GitHub. But the application is already deployed. It's not deployed. It's going to be deployed in Kubernetes, in those 2 Kubernetes clusters. So let me show you what I have. So this command, gcloud container fleet membership, it shows me that I have 2 Kubernetes clusters, one in US East Zone and the second one is in US Central Zone. So presently, if I execute kubectl config current context, it will show me the current context command shows me the current Kubernetes cluster kubectl tool is connected to. And so presently, that's my tool is connected to the US East Zone. Let's check, do I have any application instances deployed in that Kubernetes cluster? I should not, because I made sure that I deleted everything, but let's take a look. Yep, the application is not deployed yet. And this is what we are going to fix. So let me use this script. So what this script does, again, we are not going to spend time looking into the source code and YAML files. It's boring. You will be able to explore by taking the GitHub project. But this script, basically what it does, it will start my application instance in the US East Zone in this Kubernetes cluster. And these are some of the, let's say, secondary options. Like if needed, the database schema will be created. And this is my service account for Google. So what it does, basically, the script starts, you remember that my messenger presently is comprised of 3 microservices. One is config server of Spring Cloud. The second one is the messenger microservice. And the last one is attachments. So here looks like that everything was deployed successfully. So now if I execute the same kubectl get deployments command, all right, wonderful. I have all of the microservices running in my Kubernetes cluster. And if you like more, if you prefer looking at the UI, so this is my Kubernetes, 2 Kubernetes clusters in Google Cloud Console. And if you click here, you will see that we've got workloads. Workloads are my application deployments. So I have 3 microservices deployed in US East Zone. So let's do next. The application is running in the US East region, and now I want to connect to my application. Let's finally take a look at this messenger. All right, services. So I deployed the Kubernetes load balancer service. So that's the external IP address. And I will be connecting to it. Let me split the screen. All right, this way. Opening. All right, it's running. And also, let's take a look at the logs. No, not this one. So for the logs, I think, yep. I connected to this messenger application instance just to show you that the requests are served from there. So that's my username. All right, you've got something. Let's send the message. You see that Hibernate and Spring Data generate log messages. You can send something else. Spring 1. Oh, works fine. Also, we can upload a picture. Let's upload something to Google Cloud Storage. And when I do this, the messenger microservice receives this request, but then it will connect to the attachments microservice that will upload the picture into your Google Cloud Storage account. All right, it's being uploaded. Done. That's the architecture. That's what you've already seen on the slides. And here is in the logs, you see that initially the request came to the messenger, to the key microservice, and that's the IP, and that's the address of the picture that was returned by the attachments microservice. Let's try to open it. Oh, good. So we made it. But that's the only one. Right now, we deployed everything but within a single cloud region. And if that cloud region goes down, then this application instance goes down as well, and our Slack-like messenger will become unavailable. Let's fix this. So let me split the screen once again. And what I'm going to do next, let's switch their kubectl tool to my Kubernetes cluster in US Central 1 zone. Okay. So just to make sure that we did this, okay. And if I run this command right now, you'll see that I don't have any application instances, right? Because nothing is deployed in US Central Zone. And you know how to fix it. We just need to execute the same script that will deploy the same 3 microservices, the same messenger, attachments, and config server, but in US Central Zone. Let's do it. First, I need to go to my folder that stores the scripts. Okay. And now it should run fine. Wonderful. Everything is being deployed. The attachments is deployed, messenger microservice is deployed, config server is being deployed first. So why I deploy config server instance in the US Central Zone if I already have it in the US East? The same reason, if the US East region or zone becomes unavailable, my config server from the central location will be able to serve configuration to my microservices. So now let's see what's happening. All right, wonderful. All of the microservices are already deployed in their Central Zone. And let's also read the logs. No, first let's read the logs of the messenger microservice, but from the Central Zone. So what you have at the top, those are the logs from the messenger, but in the East Coast. And these are the logs of the messenger, but in the US Central region. You see that the driver is being initialized. And let's find their IP address of their load balancer service for my US Central instance. For that, we need to run kubectl get services. And that's the public IP address for the US Central Zone. And it's different, as you would see. You see, like that's 3474, that's for the US East, and 3429 is for the US Central. 2 different application instances. Let's log in. And now you can see that the logs are no longer printed in the top because we are using the application, but the logs are printed at the bottom of the screen. Because I am sending messages, I'm using the application instance in the US Central Zone. And if, let's say, I go here to their application instance in their US East, I type it here, and you would see that the logs are being updated in here, in the top. Okay, done. So what we've got so far, it literally took us a few minutes to deploy multiple application instances. So we have those application instances running in US Central and US East regions, and each application instance comes with its own public IP address. And generally that's fine, but right now we are facing another problem that can complicate, the maintenance and the usage of this distributed application. Ideally, we need to have just one single IP address that will be given to our front-end developers and to our mobile application developers that can use to connect to our backend, right? And usually for that, we use a combination of load balancers and proxies, reverse proxies. But cloud environments, like all of the cloud environments, including Google, they support a special component called the global load balancer. So the main goal and the beauty of the global load balancer is that you are getting a single IP address. That's a public IP address that will be accessible from all of the regions where your application instances are deployed. And you connect to this IP address, and then the load balancer decides what application instance is going to serve your request. Okay, for instance, let's welcome 2 more users who joined our Slack-like messenger. We have Mr. Green, a scientist from Berlin, and we have Mr. Red, a musician from Mumbai. So our application, or our front end that I've shown you, is going to use the IP address of the load balancer to connect to our backend application instances. And when, let's say, Mr. Green from Berlin opens our Slack-like messenger, his requests will be forwarded to the application instance in Europe, not in the United States. Why? Because load balancer sees that Mr. Green is physically located close enough to this application instance. And you're getting this out of the box and everything is automated. If it happens, let's say for Mr. Green, that the application instance in Europe goes down because of the cloud incident, then the load balancer will automatically forward requests of Mr. Green either to the United States or to Asia in India. All done. Now let's see how it works in practice. So what I've already done, my friends, I've already configured this load balancer as well. It usually takes 10 or 15 minutes to get it fully ready. It needs to be started. Then when it comes to Kubernetes, the load balancer is used as part of the multi-cluster ingress. And then you need to wait while the IP address, public IP address, will be accessible from all of the supported cloud regions. But if I run this command, let me switch back to my US East cluster. And if you execute this command, services, you will find that there is a multi-cluster ingress service. That's a system service that is deployed by Kubernetes, and this service responds to the requests of the multi-cluster ingress that uses the global load balancer. So, and then that load balancer decides what application instance, whether application instance from the east or from the central zone will be serving my requests. Here is this command. This command using this kubectl describe MCI geo messenger ingress command, I can find the public IP address of that load balancer. Okay, that's the public IP address. And also let me share this IP address with you in the chat. Okay, looks like I cannot share it. Yeah, for some reason I cannot share it. But anyway, you see it on the screen. It's 34, 110, 179, 193. Let me go ahead and open this IP address in my browser. But before that, let's see where the requests are going to be forwarded. First, I need to sign up once again because that's a new session through the load balancer. And if you pay attention, let's look at this part. Look at these logs. These are the logs of the application instance from the US East. So let's send some test. I'm typing messages, and you see that everything gets updated in here. Okay, which means that the load balancer that is accessible from this IP address forwards my requests to the application instance in the US East. Why? The question is why? Because I live in the US East Coast. I'm from Florida, and this application instance is closest to me, just geographically. This is why the load balancer forwards my traffic there. Yep, and right now, wonderful. Yeah, thanks, Tiffany. In the In the comments, you can find the IP address of this load balancer. You can give it a try. So the username is test@gmail.com and the password is password. So give it a try. Yeah, I see that someone is using this load balancer. I've just saw this log, which means that someone is located close enough to the application instance in the US Central, because those are the logs for the US Central location. Wonderful, wonderful. So before we do, so now what we've got, again, in 15 minutes, at least to demonstrate, you've got two application, you've got two cloud regions. In those two cloud regions, we have two Kubernetes clusters, and each Kubernetes cluster runs your application instances. The load balancer, you can use the load balancer IP address as a single point of entry, and then the load balancer will decide what application instance will be serving a user request, right, based on their location of the user. Next, returning to the question of Alexi, because it's extremely easy to deploy application instances, right, in any location of your choice. It's easy to deploy the load balancer, but what's about the database? Because the database is a little bit more tricky. With database, there is no any silver bullet solution, but there are at least 4 multi-region or multi-AZ types of database deployment, and you need to pick one based on your requirements. So you will be able to check this slide in details later, but let me quickly walk you through. As for the database, there are multiple distributed databases, and for this Slack-like messenger, we are interested in OLTP transactional databases, because that's Slack-like messenger. I cannot get corrupted data, and I have to scale. I use YugaByteDB for 2 reasons, because I work for this company. I have to talk about YugaByteDB. And the second reason, at least I'm 100% sure that all of those deployment types that I'm going to show you are supported by this database. But frankly speaking, that's not the only one database that can be used for geo-distributed applications. It all depends on your usage scenarios and requirements. So the first, the most straightforward one. You deploy a single multi-region cluster. And this is what I do right now. I have a 3-node YugaByteDB cluster that I will show you a little bit later in the United States East. And the latency for Mrs. Blue will be the lowest, because she lives in the United States. And for her, the data will be served fast enough, as fast as 5 milliseconds is possible. But for Mr. Green from Berlin or Mr. Red from Mumbai, the access latency of the data to this database will be high. It can be as high as 155 milliseconds for the round trip for Mr. Red. But at least this solution scales horizontally, right? You take this solution whenever you need to deliver high availability and good read and write performance in a selected location, and you can sacrifice, read and write latency in other locations. So this one is with multi-region database deployments. You can also deploy, when you deploy that multi-region cluster, you can define a preferred region, which means that the primary copy of your data will be stored on the nodes from that region, and when you run multi-step transactions or requests with joins, etc., all of the data will be served from that region. That will help you to minimize traffic between your multiple regions. But when you write data, again, writes by default go to the preferred region, and from the preferred region, they are synchronously replicated to your other locations. Another option is when you still have a single multi-region cluster in one of your primary locations. And this is a scalable and fault-tolerant solution. It provides fast reads and writes in the United States, like it's shown here. But you're saying that for my Slack-like messenger, what we do most of the time, we check the discussion, right? We check what people have written, and then only then we try to respond. Which means that if you want to improve read latency in distant locations such as Europe or Asia, then one of the appropriated solutions, and you know that solution, you can deploy read replica nodes. Those read replica nodes, such as those you see in Europe and Asia, they are attached to the primary cluster, and all of the changes are sent asynchronously from your primary cluster to your read replica locations. In this case, again, you are achieving at least good read latency across all of their supported regions. But with asynchronous replication, as a trade-off, there is a data lag, time lag, because the changes are sent asynchronously from your primary cluster, and the performance for writes will not be good enough in Europe and in Asia. Another solution that is used very often, and we use it with not only with distributed databases, but with traditional databases, you can deploy multiple standalone database clusters. For instance, you can have a standalone cluster in the United States for the United States user. You can have the same cluster in Asia for your customers from Asia. And that will work for many scenarios. The only one disadvantage that might exist for some of the applications, if you need to query data from all of those clusters, then you need to connect to all of those databases, get data, merge this data somehow, use some third-party solution for federated queries, or implement it in your application. And also the changes are sent asynchronously, but at least this is also a good and feasible option. For my Slack-like messenger, how it works by design, it has to function across the continents, because like Slack has to function across the continents. And my database also needs to be deployed. Database nodes need to be deployed in all of the primary locations. There is another, and here is, let's quickly talk about a geo-partition cluster. This is a type of the deployment that is supported by distributed SQL databases. You have a single cluster, like here it's deployed across the United States, Europe, and Asia. But in your, talking about trade-off, right? There's always a trade-off, remember. In your application schema, in your table, you have a custom column. And in my case, the column is named region. Based on the value of the region column, the data will be placed automatically in one of the locations or served from one of the locations. For instance, when Mr. Green sends messages into my Slack-like application, then the application instance will be sending all of those writes and serving reads from the nodes in Europe, because the region is set to European Union. So the database sees that, all right, the region value is European Union, then the data is located in these nodes. And this is how you can deliver fast reads and writes based on your customer location. And this is also good for the data regulations, because data of the European customers is stored on these nodes. But again, it's a trade-off. You need to introduce a custom column in your application. So the name is up to you, and the values are up to you. It can be city name, it can be data warehouse name, or anything else you'd like to have in your application. So let me quickly show you the database, and then we are going to do the fault tolerance demo, because this is our solution. So this is what we created. We are not discussing, streaming an API component, but if you need it, you can always introduce it using Spring Cloud framework or any other third-party solutions. But anyway, your application instances in the location of your choice, your database, your data also has to be located close enough to your applications, so that if anything goes down, the database still functions and the data is served as fast as possible. Now, the database for this demo, I'm deploying Yuga by DB in Google Cloud as well, in 3 regions: US West, US Central, and US East. This is what I do. And US East, I think, is set as a preferred, US East is a preferred region, meaning that by default, the primary copy of the data is located in this region. And the backup data is synchronously synchronized to the US Central and US West. So now let's do the demo. So what I do, that's my IP address of the global load balancer. Let's do the test. Okay, you see that the application instance from the east is responding. Now, let's kill that application. Let's simulate a regional outage. I cannot shut down the cloud region in Google, but at least I can simulate that outage by bringing down my primary microservice. The microservice the load balancer is connecting to make sure that whether that microservice is available and whether it's capable of processing user requests. So, yep, I am in the US East. So now, kubectl get deployments. deployments. So that's my microservice. I need to kill it, and they will do this harshly. kubectl delete deployment. All right, it's deleted. All right, no. And you see that, okay, the logs are no longer connected, the application instance is down. And now let's see what's happening. What's going to happen? This is my load balancer. Let me type a message. Oops, you see a redirect. What happened? The load balancer detected that the application instance my session was connected to is no longer available because that region sort of is down. And the load balancer redirected my traffic to another application instance, which is in the US Central Zone. So now let's take a look, pay attention to this screen. These are the logs of the application instance from the US Central. So let me connect. Good, you see the logs? The application is up and running. So the only one this inconvenience was that I need to sign in twice. But again, you always can have a session replication solution if you don't want to have that. And generally, everything is up and running. So I was not stopping, the database nodes, but the same if I stopped YugaByDB node in US East, nothing would be happening because the other two nodes will be serving my requests. So generally speaking, this is how it works. You deployed your multi-regional application, and even when you have the load balancer, you have a distributed data set. And if any outage happens in your availability zone or in your region, with this architecture, the user traffic can be automatically redirected to live, healthy application instances by the load balancer. And also the data will be served from your globally distributed database, because a distributed database always keeps more than one copy of your data. All right. So to finalize, how do you start? Because today I was showing you the multi-region configuration. Then on the slides, you've seen how database and application instances were deployed across several continents. But how do you start? At least the best way to start, if you don't need to deploy your application across multiple regions right away, but deploy at least it within several availability zones within a single region. Okay, so you create a new application or you need to modernize an existing one. Just take this framework to practice. Make sure that when you run your next version of the application, it functions across multiple availability zones within your region. And do the same for your database. So then if any of the availability zones goes down, you are up and running, you're happy, right? And then if it happens, and usually this happens, when you will be requested to scale, someone can come and tell you, right, man, we're getting many more users right now in the US East Coast. So we need to serve user traffic faster from there. You will be able to scale this architecture, expand this architecture to the east from the west by deploying additional application instances and by deploying your database, right? All right. So what else? These are different resources that you can take a look. If you would like to learn more, just check the slides. Designing data-intensive applications, architecting for scale. Architecting for scale is focuses on the high availability. Brilliant book to check. If you are interested in databases, but never, let's say, had a time just to understand the internals, check Database Internals, which is written by a database expert for application developers. YugaByDB University free courses for distributed SQL if you need to migrate or thinking of migration from traditional databases to distributed SQL ones. And if you have any questions on this topic or anything related to distributed databases or Geo-Distributed applications, you can find me on Twitter. So Tiffany, looks like we ran out of time, right? Can I take any questions or what's the best way to move forward?
Definitely. Yeah, so there's a question in there that's asking if we can use MySQL instead of Postgres.
So in this when it comes to YugaByDB, I mean, generally speaking, when you create any application, you are free to use whatever you want. It can be MySQL, it can be Oracle or Postgres. When it comes to Geo-Distributed applications, you can certainly attach, let's say, read replicas to your MySQL deployments, or you can have, let's say, your primary MySQL instance and your standby MySQL instance. It depends on your requirements, right? If the primary MySQL instance goes down, then it will take some time for you to switch to the secondary MySQL instance, and also think about data lag. How it's different from YugaByteDB. YugaByteDB is built on Postgres, and it provides several multi-region and multi-Z deployment options. So if you want to, what it means for you, if you use Postgres and then you need to migrate to a distributed SQL database, then it would be easier to do that with YugaByteDB, because YugaByteDB is built on the PostgreSQL source code. If you need to migrate from MySQL for any reason, right, to a distributed SQL database, such as YugaByteDB, then we have tooling for that. You're not built on MySQL. You might need, let's say, to change some of your source code if you're using MySQL-related syntax, but nevertheless, it's all possible. Probably I've got your question right. If not, then clarify it, please. Okay, I no longer hear you, so something is...
I'm muted. Is there a strategy to replicate DB on several zones and deploy services only if the primary zone is going down?
So when it comes to data running database on several availability zones, my actually advice, like here, even if to take Google Cloud Platform as an example, the latency between availability zones within a region is just 5 milliseconds, just 5 milliseconds to get from one availability zone to the other. So if you deploy your application just within one region across multiple availability zones, then just deploy a single database cluster across those zones, and you will get draft-based synchronous replication. It always will be consistent. If any of the zones goes down, if any of the nodes goes down, your RTO, recovery time objective, is just 3 seconds. This is how quickly YugaByteDB cluster internally can start forwarding database requests to the nodes that survived an outage. So for availability zones, probably I would take a look at this, unless you're developing trading platforms, because for those, 5 milliseconds latency between those might be way too high. But for other applications, 5 milliseconds, round trip time between availability zones is not that big, usually. And you say that in deploy services only if primary zone is gone. Is there a strategy to replicate? That was their database, and deploy services only if primary zone is going down. You can do that. I mean, it's so, Alexei, it all depends on your when it comes to high availability, you need to pay attention to the two requirements: recovery time objective, and also another one is called, that basically tells you how much of data you can lose. Recovery point objective, RPO and RTO. Some of the applications have to have RPO, recovery point objective, equal to 0, which means that no any data loss is possible. So like whatever happens, we cannot lose any update. And for them, you have to deploy your database and application instances across all of the availability zones. But if your RPO, let's say, is 20 seconds, which means that I can lose, just 20 seconds of updates, then you can deploy, let's say, primary database node, primary application instance, and then replicate your database changes to another location asynchronously. Just take a look at those two requirements first: RPO, recovery point objective, and RTO, recovery time objective. Based on those requirements for your application, you can properly pick between your multi-AZ or multi-region database deployment and multi-AZ or multi-region application deployment.
And then I actually had a question regarding the logging. So in the bottom left, it was talking about like failed to apply load balance, but you had a load balancer. So what was with that warning that it was having there?
This one, probably this warnings.
Let's see. Let me move us out of the way. There we go. It was higher up, like, it had it beforehand, but yeah, in the bottom left, it was giving a warning
Yeah, probably
that I'm
this
guessing
warning.
was written in there.
Yeah, like this warnings.
Yeah, what is
So what it means,
that
what
one's
it
a little
does. So
different, but the one right above
yeah,
it,
this
yeah.
is a harmless warning. This is the warning from the Yugabyte DB smart driver. This smart driver collects IP addresses of all of the Yugabyte DB nodes and tries to connect to them directly. But this warning says, like, when I deploy Yugabyte, I can deploy Yugabyte DB is open source, meaning that you can take it and use it for free, deploy it or whenever you'd like. But I'm using today Yugabyte DB managed. It's just a cloud version, and this one comes with a single IP address. And this single IP address is a load balancer. So when the driver connects to this IP address, then it executes a special function over the database, getting their internal IP addresses of your database nodes in West and Central. And it cannot connect to those nodes directly. Because with Yugabyte DB managed, the application always connects to one of the public endpoints like this one. And then this endpoint decides what node will be serving your request. So generally, that's the warning. This warning, yeah, I agree that it's a little bit confusing. It's
Yeah, and it was the one, like,
it's
2
a
above it.
usability issue. It's a developer experience issue. That's what it is. But it's harmless.
Got it. I figured
A
it
good
was,
eye. Have a good eye.
something that was added there since I saw that connection didn't have CON, so it's just action or something like that, and I was just like, "Wait, this has to be an added, warning."
Mm-hmm. No, it's fine. It's fine.
That was cool though, like, just, like, seeing, like, that it told you, like, where the person potentially was closer to or whatever, and being able to just, like, actually interact with, like, a demo.
Mm-hmm. Yeah, that's right.
But yeah, thank you so much for doing this. And thanks everyone for coming and asking questions, anything like that. And this will be up on multiple different YouTube channels, the VMware Tanzu Spring Developer, and it's also on Twitch. So if you feel like watching this again later, or if you're actually watching this later and not seeing it right now. But yeah, thanks again so much. And so we have a few different things that I wanted to bring up before we fully end the stream. So, first we have Spring Academy. So basically, if you want to take some classes, like little tutorial type things online that you can walk through, some hands-on stuff, if you go to spring.academy, you can go check that out. And also, as I mentioned at the very beginning, we have Spring One at VMware Explore. So please come join us in person on the, and it'll be like August 21st through 24th over in Vegas. So yeah, thanks again, everyone.